Based on the experience of a drilling contractor in a given area, a string of drill pipe is expected to last a certain number of feet drilled. A part of the cost of replacing the string is taken from the gross profits made by the contractor on each well and is laid aside until the total cost is recovered. Consequently, if the string's life does not last as long as expected, the contractor is faced with buying a new string without having recovered his cost, and any net profit derived from drilling a well is reduced accordingly or is wiped out altogether. Whether or not the drill string lasts its expected life depends to a large extent on how drilling crews take care of the string during handling and running. Taking time out to care for the drill string runs counter to the driller's creed that the faster you get her on the bottom and turn her to the right, the faster you'll make money. But in truth, there must be a balance between the two. Thus, the object of this presentation is to help establish that balance by showing how the string should be taken care of and what some of the indications and results are when it is not. But before we get too far along, let's get into a little nomenclature so that everyone will know what we're talking about. The body of a joint of drill pipe is usually made of seamless steel tubing. Sometimes it is made of aluminum. The tube ends are upset, that is, thickened, either internally, externally, or both internally and externally, to increase the strength at that point. Then, flash or friction welded onto one upset end of the tube is a special threaded and shouldered male fitting called the tool joint pin. Its female counterpart, welded to the other upset end, is the tool joint box. These are sometimes referred to as rotary shouldered connections. Thus, the tool joints enable lengths of drill pipe to be screwed together in order to make up the drill string, which is part of the drill stem used to transmit drilling fluid to the bottom of the hole and turn the bit. Thus ends the lesson on drill string nomenclature. Now to continue with care and handling. Most joints of drill pipe are handled in the rotary table by elevators that latch around the pipe and mate with the tapered shoulders located at the base of the tool joint box. The tapered shoulders on the box are manufactured having either an 18-degree taper, as shown, or a square. The 18-degree taper is most common on regular strength drill pipe. This degree of taper better reduces the concentration of bending stresses where the limber body meets the stiffer body of the tool joint. It also helps to guide the tool joint around obstacles, such as rocks and ledges, in the hole when tripping in. A square lifting shoulder is used most frequently on high-strength drill pipe where the elevators are used as spiders to suspend the drill string in the rotary instead of setting slips. Tool joint pins are generally furnished with 35-degree tapered shoulders, but are available with an 18-degree taper. The 35-degree taper can be machined down to 18 degrees, but there will be a reduction of Tong space. The taper on the pin may also be used by the manufacturer and the drilling contractor as a place to identify standard weight grade E pipe. It is recommended that the steel die stencil be placed nowhere else. Care should be taken to see that the stencil on the taper is no taller than 3/8 of an inch and is placed on the flat portions well above the radius of the taper where it curves to meet the pipe. Placing the identification stencil on the box end taper is also permissible. However, it would probably be quickly scoured away by sand-laden drilling fluid. Also, most box end tool joints have hard facing applied on part of the taper and part way up the box, making it difficult to properly position the stencil. The hard facing is composed of tungsten carbide particles in a welded matrix. It is put there to reduce fluid erosion and circumferential wear of the box and adjacent pin on the wall of the hole. The facing should be ground down smooth so that it will not score or wear holes in the casing. Standard weight grade E high-strength drill pipe at left has a flat milled on the tool joint pin, opposite an identifying groove from the pin threads. Code numbers for the pipe's weight and grade are stenciled on the flat. Heavyweight high-strength drill pipe at right has the groove turned on the end of the tool joint pin opposite the threads. The flat is milled in the middle of the tong space. Both are marked so they can be read while hanging in the elevators. If the tool joints are manufactured under API specifications, and most are, the thread form, lead, and taper per foot are standard, so that one manufacturer's tool joint can be made up on the same size tool joint of another manufacturer's. This design permits easier stabbing than non-tapered threads, and, once stabbed, fewer turns are needed to make up the joint, because the threads on the pin do not engage the threads in the box until the pin is about 3/4 of the way in. On makeup, the shoulders at the base of the threads on the pin, as at upper left, and the upper end of the box below, come together and are compressed, thus making the only seal against drilling fluid leaking out of the joint. As indicated, but exaggerated in the circle at right, the threads do not seal against leakage because one flank of the thread in the pin is pulled away from that in the box, leaving a spiral opening from inside the tool joint to the shoulder. The only seal is provided by the shoulders coming in contact. As drill pipe arrives from the tool joint manufacturer or from a supply company, it may or may not be stored in the drilling contractor's yard. If it is temporarily stored, certain precautions should be observed. The racks should be spaced so that the body of the pipe, not the tool joint or upset, rides on wooden stringers. A stringer in the middle of the pipe keeps the pipe from sagging. All racks should be reasonably level and hold the pipe at least 18 inches from the ground to keep the moisture and dirt off the pipe and provide good ventilation from below. Wooden strips of equal thickness should be provided between layers of pipe and directly over the 3 ground supports so that no weight rests on the tool joints in the lower tiers. Each layer of pipe should be secured by nailing blocks to both ends of each spacing strip to keep the pipe from rolling. For purposes of safety, drill pipe should not be stacked higher than 10 feet, or at the rig, no more than 5 tiers high. Staggering adjoining lengths of pipe, an amount about the same length as the tool joints, allows more joints to be placed in each layer and keeps the tool joints separated. Here, for example, the tool joint beginning at left is staggered a tool joint's length in front of the joint to its right. Likewise, the second joint is placed a tool joint's length in front of the third, and so on. When the pipe is moved out to the rig, the pipe should be loaded so that all the tool joint pins are facing in one direction. Then, when it is unloaded at the rig, the boxes will be on the rig side of the rack. Care should be taken to space the joints on the truck so that there is no chafing of tool joint shoulders or pipe by the hard banding on adjacent joints. The pipe should be securely tied down with suitable chain. Preferably, the chain should be above the truck's bolsters. If the pipe has a long way to go, it would be a good idea to tie down the middle of the load with another chain. When unloading at the rig site, make sure that the thread protectors are tightly in place to protect the threads and sealing shoulders from any rough handling. Use a gin pole if possible. Unload 1, 2, or 3 lengths at a time. This depends on the number that can be fully controlled. Always use a sling that supports the pipe at 2 places. API recommends that the legs of the sling be long enough to place the hooks in the protected ends of the pipe or near the tool joints. This bent joint of pipe shows one of the things that can happen if only a single line is attached to the middle of the pipe. Other damage can occur too, like if the pipe gets snagged on the truck or rack, during the lifting process. Also, the pipe is harder to control with just one line. When unloading pipe by hand, use a snub line to control the roll of the pipe down the ramps. 2 or more lines would be better to keep the pipe parallel to the stack. Do not let the pipe gather momentum and strike the ends of other joints. Even with the protectors in place, there is danger from a heavy blow damaging the threads, cross-threading a protector, or turning the edge of a shoulder. Stop each length before it reaches the preceding length and then push together by hand. At some point along the line, records concerning this string's life and performance should be started and maintained. The cost of pipe places it in the category of a capital investment, and its life is relatively short. What better time is there to start than when the pipe is on the rack, at the rig, and before it is even run in the well? The minimum items that the records should reflect are the expected and actual life, type of service, and any severe stresses to which the string has been subjected. Some records are much more elaborate, showing a special number for each joint, its individual wear pattern, and so forth. Just prior to running or adding pipe to the string, the pin and box threads and shoulders of each joint should be thoroughly cleaned and visually inspected for damaged shoulders and threads. Cleaning should be done with a suitable solvent and brush. The initial cleaning can be done with a wire brush. Final cleaning should be done with a bristle scrub brush because it cleans more thoroughly. Cleaning pays off in 3 ways. First and foremost, it removes foreign material, permitting proper makeup. Second, it permits better inspection. And third, it increases life of the connections by elimination of such abrasive materials as sand and dirt. Make sure that thread protectors are cleaned and reinstalled on both box and pin ends, but especially the pin end. Made up hand-tight, protectors prevent most of the damage that occurs in moving the pipe onto the catwalk and up the ramp to the rig floor. Keep the catwalk and ramp clear of all obstructions. Do not allow the threads or shoulders of tool joints to strike metal on the catwalk or ramp when picking up the pipe. Note here the vulnerability of unprotected threads and shoulders to the seams that are welded in the steel floor of the catwalk. Be careful as the pipe is swung over the hole to ready it for stabbing. Swinging pipe out of control can do great damage, not only to the pipe, but to the floor personnel as well. It is extremely important to break in new tool joints correctly because the newly machined surfaces, although they look polished or have a coating applied, still have microscopic size wickers, burrs, and high spots that are easily heated to fusing temperature by a fast makeup. Galling is the result. So, unless care is taken, a new string of drill pipe can be ruined the first 2 or 3 trips. If care is taken, the newly machined surfaces become work-hardened after several trips. Then, normal makeup speed can be resumed. Galls are the result of 2 actions. First, there is the heating of high spots on the surfaces, as at the arrow, during makeup. Second, these heated high spots fuse together and cool. There is no sure way of knowing this is happening unless there is a chattering sound from the tool joints as they are spun up. The actual galling takes place when the fused metal is torn apart during breakout. Thus, galling is usually indicated when a tool joint is hard to break out. Small galls that are not repaired or removed result in high spots, as shown by the arrowheads. These galls make it difficult or impossible for the shoulders to make up properly, eventually allowing high-pressure drilling fluid to escape and erode away the threads and shoulder. To maintain trouble-free tool joints on new pipe or on pipe added to the string, these steps are essential. 1. Clean and dry threads and shoulders. 2. Inspect threads and shoulders for damage. 3. Lubricate the threads and shoulders with the proper compound. 4. Make up and break out new joints slowly for the first 2 or 3 trips, after which the operation can be sped up. And finally, rotate brakes, that is, break the string at different joints each trip so that all connections can be visually inspected over a 3-trip period. After this initial cleaning of threads and shoulders, subsequent cleaning during trips is not necessary under normal circumstances. With the threads and shoulders of a new joint or an added single inspected, cleaned, and dried, tool joint compound or dope is applied to the threads and shoulders of both the box and pin. Dope provides a separating film and prevents galling. It should be applied with a round, stiff-bristled brush. Care should be taken to cover all the threads, and especially the shoulders. Do not expect the makeup to distribute the compound evenly on threads or extrude onto the shoulders. Thread compounds containing 40 to 60% by weight of finely powdered metallic zinc are recommended for tool joint connections. The compound should never be thinned. Thinning reduces the metal filler and the compound becomes ineffective. Thread compounds for tubing or casing should not be used on tool joints because they are slick and allow the joint to be over-tightened with a low-torque application. Keep the compound and brush clean and free from dirt and sand, and don't forget the last swipe on the tool joint shoulder. Teamwork plays a big part during stabbing, and coordination must be exercised between the driller and the floorman. Allowing the pin to bump the shoulder can cause an indention on the shoulder. The indention may destroy the ability of the shoulders to seal and result in a leak and eventual washout. If the pin does land on the shoulder, don't just roll it off. Pick it up, inspect the shoulder, and if there is no damage, stab again. If there is damage, repair it with a shoulder dressing tool or take the joint out of the string until it can be taken to the shop for repair. If a pin is rolled or forced off the shoulder and allowed to drop into the box, the engaging threads may meet with such force that they are seriously bent or damaged. Once new tool joints are broken in, they may be spun up with a spinning line or chain, or with spinning tongs. If a chain is used, care should be taken to see that the chain does not hang up or become pinched between the box and pin shoulders and cause thread or shoulder damage. If the joint wobbles because it is bent, the joint should be laid down until it can be straightened, because a crooked joint is very susceptible to wear and fatigue. When the tongs are applied, be sure the tongs engage the body of the box and pin outside the hard-faced area and not on the upset or body of the pipe. The tongs may slip on the smaller diameters and peel the pipe, or put transverse scars on the pipe where stresses and fatigue failure may set in. 2. Be sure the gripping surfaces of the tongs do not overlap the tool joint shoulders, which could result in a rift or high spot and a poor seal such as this. Proper tonging procedures also produce a longer, trouble-free life for the drill string. Be sure the tonging and torque measuring equipment is in good working order. Use recommended API makeup torque from tables relating to the pipe you are using. Avoid forced makeup of improperly engaged threads. Recommended makeup torques for the various sizes, types, and classes of tool joints are available from tables. API provides these tables in their recommended practice for drill stem design and operating limits, publication RP7G. These are also available in the IADC drilling manual. Proper tonging ensures that the shoulders of the pin and box are compressed to such an extent that they will not separate under the hanging load imposed by the pipe below. Proper tonging also ensures that the tool joints are not made up so tight that the pin stretches permanently or bells the box. This pin and this box are the result of a joint that was not made up tight enough. The shoulders separated and allowed movement between the mating surfaces of the box and pin. The high pressure of the drilling fluid being pumped down the string washed out the thread compound and started erosion of the threads and shoulders. And here is an example of over-tonging. Notice to the right how the thread gauge rests almost exactly on top of the threads of this sectioned pin. Then, moving to the left, notice that the gauge begins to fit into the pin threads. When the shoulders on the box and pin meet during makeup, they resist further makeup, but the threads are still free to advance, placing the pin under tension. If the tension goes beyond the yield point of the metal, the pin will be permanently stretched, as this one is, and will not return to its original length the next time it is broken out. In fact, excessive tonging can actually pull the pin in two. The cupped appearance of the surface of the fracture, especially on the pin at right, is indicative of this type of failure. The proper tightness of tool joints is best indicated by the proper use of Tong torque indicators. There are several types of Tong torque indicators in use today. This cam-type indicator is mounted in the Tong pull line and is preset at the desired pounds of Tong line pull. Then, each time that amount of pull is reached, the indicator issues a loud pop. The hydraulic torque indicator has a hydraulic cylinder and a pressure gauge. The black pointer indicates the amount of line pull in pounds. There is also a red pointer that can be preset to the amount of pull desired. Here, for example, it is set at 2,000 pounds. This gauge can be calibrated to show foot-pounds of torque if the effective length of the Tong arm is known. But in general, Tong torque indicators indicate pounds of line pull, not foot-pounds of torque. No matter what type of Tong torque indicator is used, there should always be a 90-degree angle between the Tong handle and pull line at the final torquing moment to get a true reading on the torque indicator. Any other angle at the final torquing moment reduces the length of the Tong arm and causes the torque indicator to show an erroneous reading, one that will be less than the torque desired. Take, for example, as at left, a Tong with an arm length of 4 feet and an indicated Tong line pull of 3,000 pounds. Then calculated as below, 4 feet times 3,000 pounds equals 12,000 foot-pounds of torque. If the Tong arm is more than or less than 90 degrees to the indicated line pull, as at right, the effective Tong arm is shortened, say from 4 feet to 3 feet. As a consequence, the foot-pounds of torque is reduced, as calculated to 9,000, even though the indicator shows that the line pull is 3,000 pounds and that the joint is made up to the correct tightness. With the joint or stand made up to its correct torque, the drill stem is raised, and the slips that held the drill stem suspended in the hole are pulled. When the elevators come down, the slips are again set to suspend the pipe in the hole. This takes precise coordination between the driller and his crew because the pipe must be stopped before the slips are brought into play. Catching the drill pipe while it is in motion will, as at A, stretch and bottleneck the pipe. The slips at B act as swedges to elongate the pipe in the slip area. Also, a worn rotary table and master bushing can damage all of the joints in the string. As at upper to lower right, the taper on the bushing changes as the table and bushing wear and allows the slips to set too far down into the bowl. The slips, under load, become deformed, and their gripping area is reduced to a point where hanging and stopping loads bottleneck each joint of pipe that's hung in the rotary cable. So, drill pipe care and handling also involves equipment maintenance. When the last stand of drill pipe is run into the hole during a trip, the kelly is made up of the string to continue drilling. But before the kelly is made up, the mud from the rat hole and old thread compound should be cleaned off the kelly saver sub, and the sub thoroughly inspected for shoulder and thread damage. Over a period of time, this sub may be made up on every box in the string, and if it is damaged, every box will be affected. Also, the kelly should be inspected for absolute straightness to prevent eccentric tool joint wear and damage to the bore of the blowout preventer stack. Once the bit is back on bottom and drilling, it is up to the driller to apply the proper techniques of drilling to take care of the drill string. Of utmost importance is to keep the drill pipe string in tension with only the collars in compression, thus preventing the drill string from corkscrewing in the hole. Rotary speed is also an important factor. Tests have proven that drill strings, when rotated at certain speeds, begin to vibrate or develop a harmonic motion. This harmonic motion is similar to the motion of strings that are plucked on a guitar. This undesirable action stresses all parts of the drill string and can be detected as rough running or as intermittent torquing up of the string. The remedy is to speed up or slow down the rotary. If this does not help, then the cause can be contributed to the formation or bit. Harmonic motion can also wear down one side of the pipe until it bursts or collapses under some adverse condition. And remember to properly torque each joint as it is made up in the string. If too much torque is used, it may result in a belled-out box and overly made-up pin. API recommends that any box swelled greater than 31 thousandths of an inch or any pin stretched more than 6 thousandths of an inch should be sent to the shop. In extreme cases, tension due to excessive torque can cause the box to split. It's downhole, while drilling, that most troubles develop from the improper care and handling of the drill string at the surface. It's downhole where the greatest stress forces, such as torque, bending, and axial loading, take place. If there is any weakness in design, or if part of the design is negated by careless handling techniques, it's at that point where trouble will develop and propagate. Metal fatigue is usually the result. Metal fatigue results from a concentration of bending stresses at a scratch or notch running 90 degrees, more or less, to the stress lines. It is hastened when the stresses are applied and then relaxed in a cyclic fashion, as indicated at left. The matrix holding the grains of metal together is pulled or torn loose at the base of the notch. A smaller, microscopic crack appears at the deepest part of the notch and propagates with each bending cycle toward the opposite side of the metal, until, as at lower right, the strip fails. The sharper the notch is, the quicker it will fatigue. Notice that the notch resembles the root of a thread. Now let's compare the notch failure to something we know. Let's assume that this box, damaged by tongs, was not pulled out of the string, but instead was tonged up to the correct torque and run into the hole. The high spot on the shoulder, which is exaggerated here, holds the pin and box apart, allowing the connection to bend as it is rotated in the hole. The weakest point in a made-up tool joint is at the root of the last engaged thread, indicated by the arrows. Consequently, the bending stress concentrates there, and the pin or box crack and eventually fail from metal fatigue. The last engaged threads are, in effect, notches. A fatigue crack in the body of the pipe or a tool joint washout can be detected downhole before the string parts if the driller is alert enough to detect the steady drop in mud pressure that will occur. If a washout is thought to be the cause, the kelly is broken out and short pieces of knotted soft rope or strips of rag are put in the drill pipe. Then the soft rope is pumped down the hole. When pump pressure is regained, it means the soft rope has plugged the hole. And when the pipe is tripped out, the protruding rope or cloth fibers make the washout easy to find. Early warnings of pipe failure can also be observed by an alert drilling crew while coming out or going back into the hole. The most experienced floor hand should be aware of these warnings and be assigned the duty of calling the driller's attention to them. Ordinarily, the earliest warnings of impending tool joint trouble is a dry or muddy pin. This indicates that the joint was not made up pressure tight, allowing drilling fluid to leak. The fluid is displaced or washed off. When a dry pin is found, both the joint of pipe it is on and the joint of pipe it was made up on should be laid down, inspected, and the cause of the leak remedied. If the problem is not corrected, then the joint may be eroded and cut out when it goes back in the hole. Crews should also watch for OD wear on the tool joints. Wear like this indicates that the tool joint is rubbing on the sides of the hole. It may be caused by a crooked hole or by running the rotary at a speed that causes harmonic motion in the string. When coming out of the hole, just as when running in, the slips should be set after the pipe has been stopped. Use slips with serrations, preferably with pyramid-shaped teeth, to prevent circumferential cuts on the pipe. Use 2 sets of tongs to break out or make up the joints. The breakout torque should be 80 to 90% of the makeup torque. But if the joint has been torqued up tighter down hole, using only 1 tong to break it out could bend the pipe or cause the pipe to turn in the slips and cut transverse scars in this critical area on the drill pipe. Spinning the joint out with the rotary table could also scar the pipe, especially if the string below the slips is not heavy enough to cause sufficient wedging action of the slips against the pipe. When breaking out, enough tension should be maintained on the hook spring to lift the tool joint pin free of the box when the threads disengage. Too much tension could cause the stand hanging from the hook to bounce and drive the pin back into the box or land on the shoulder. Such a heavy blow, although momentary, certainly calls for an inspection of the threads and shoulders for damage. When standing the pipe back, make sure that the setback area is clean of tools, wrenches, subs, and other hard objects that could get in the way or damage the tool joint threads. If the pipe stand does not line up satisfactorily, use only a recommended pipe jack, one that supports a large area of the tool joint shoulder. Once the well is drilled, the drill string is laid down. Here, too, the drill pipe should be handled with care so that it will be in good condition for the drilling of the next well. Install thread protectors, preferably before laying the pipe down, and be sure the protectors are made up tightly. In bringing the pipe down off the rig floor, keep the tool joints from striking other pipe or metal on the ramp or on the catwalk. When rolling the pipe from the catwalk onto the racks, check for straightness and lay aside any crooked joints so they can be straightened. Also, wash the tool joints and the drill pipe inside and outside with clear, fresh water. This removes any corrosive agent which might bring about rapid deterioration. Pits on pipe, both internal and external, are sites from which fatigue cracks can propagate. Then lubricate the threads and shoulders, preferably with a rust preventive, if the drill string will be stored for any length of time. If thread protectors have been removed, replace them. If they have not been used up to this time, install them. All rubber protectors should be removed if the storage period is to be for very long. A circumferential groove can be caused by corrosion at the ends of the rubber protectors when they are left on. This situation occurs quite frequently on grade E and high-strength drill pipe. When the drill pipe is on the rack between wells, it is a good time to check all of the drill string. Tool joint damage, such as slight crowning of the shoulders, dents, upsets, fins, and galls, can usually be repaired on the rack at the rig with available hand tools, but care must be taken not to remove too much metal. When using a triangular file on thread damage or galls, make sure that the corner of the file does not cut into the thread root, creating a sharper notch where metal fatigue is likely to take place. Tool joint shoulders, even though they show no obvious damage, should be checked with a flatness ring. Clean the shoulder thoroughly, then hold the ring against the shoulder, applying finger pressure at points 180 degrees apart, and attempt to rock the ring. Repeat at points 90 degrees from the first point of pressure. If the ring rocks at all, then it will be necessary to smooth out the high spots using a hand-type dressing tool. Be sure the tool is the right size, does not wobble or slip, and be careful not to remove too much metal. Circumferential machining rings are permissible, but humps, galls, rolled edges, and indentions running radially from the center to the outside are not permissible. A flat file, if used correctly, across both sides of the tool joint is satisfactory. File down only the damaged section. Do not attempt to remove metal from any other place, and use the flatness ring often. API recommends that qualified inspectors periodically inspect, evaluate, and grade the condition of the drill stem. The cross-sectional area of the tube and tool joints, average minimum wall thickness, slip area diameter and appearance, eccentric wear, condition of threads and shoulders, and the presence of pitting and fatigue cracks are all checked. Much of the inspection may be done with visual, magnetic particle, radioactive, or sonic methods. The total procedure allows a determination of the usability of each joint of drill pipe for specific applications. During inspection, color-coded bands and stripes are applied to each joint of the drill string inspected. On the outer ends of the tool joints are stripes denoting the classification of each. The stencil on the taper of the pin has been discussed before. Tool joints and drill pipe found suitable for medium-depth, non-directionally drilled wells are termed normal surface and are graded Class 1 and are color-coded with one white band. If the drill pipe is found to be suitable for drilling deeper wells or for use in directionally drilled holes, the pipe is graded premium class by API classification standards. Such pipe is color-coded with 2 white bands. Those banded with yellow, blue, and green can be placed in progressively more limited service. Those banded red have fatigue cracks or are scrap. Tool joints that are field repairable are striped green. Scrap or shop repairables are striped red. The drill string is expensive, and the expense is prorated to the footage the string is expected to drill. If it doesn't, then the replacement cost is taken out of the profits that may be wiped out, even though the welds were drilled in less time than called for by the contract. Therefore, drilling crews must be as efficient in the care and handling of the drill string as they are in making holes. A little effort on your part can make a big difference. So please, handle with care.